The next speaker is Dr. Farooq Khan. He's currently president of Samsung R&D America, where he manages research in the areas of wireless communication, RF antennas, analog sensors, and mobile services. Dr. Khan got his PhD in computer engineering from Université de Versailles in France. I can't speak French. So he held research position with Bell Labs in New Jersey and Ericsson Research in Sweden. And he has authored more than at least 40 research papers and holds over 100 patents. He must have enjoyed writing patents. He also is the author of a book, LTE, for 4G mobile broadband. So if you have any LTE question, you have a person here. Dr. Khan, please.
Thank you for the introduction, and it's a pleasure to be back here. This is my second trip here this year. I don't travel much, only a few trips per year, so I can attest to Sujit's and Lon's persuasion skills making me come here another time. The first time I was here was in 2011. In Samsung, we have been doing research on millimeter wave mobile communications for the last 5 years. And earlier 2011, we presented our first results on millimeter wave mobile communications in a conference. After that, Professor Bhaskar Rao invited us here, and that was literally the second presentation on using millimeter wave for mobile communications. And now it's exciting to see CWC trying to take a leading role in furthering 5G research. So we have been hearing a lot about connecting everything. I think very nice presentation from Daniel. But I also want to emphasize, first we need to connect every being. And once we are able to connect every being and everything, how we can solve the top problems that humanity is facing. I think Daniel did a great job setting the stage, how machines and humans working together were able to win the chess competition. But rather than solving chess problems, let's look at some of the problems that humankind is facing. So this is a list of top 10 problems listed by Richard Smalley, Nobel laureate, in almost 10 years ago. And it hasn't changed. Every time he would give a talk, he will ask the audience, what are the top 10 problems? And always come up with the same list. I have tried in my own team. You can go and try. These are the all 10 problems everybody comes up with. The problems are very well defined also. And earlier we said problem definition makes most of the part of the solution. But we are not able to solve these problems. Actually, situation is worsening. You can look at energy, water, food, environment, poverty. Yes, there is some improvement in poverty, but the problem is disparity between rich and poor. So how we can use, once we are able, with 5G, we are able to connect every being and everything, how we can solve these problems. So the way I have been thinking is maybe we as humans are running into our limitations. We evolved in small communities, like a tribe or 50 or 100 people. Now in a global world where we are facing global problems, we need a new paradigm to solve these problems. And to understand that, let me start with this, what I call data, information, knowledge, and wisdom paradigm. So data is just symbols and numbers without context, while information puts data into context. And when you see the patterns in information, knowledge is created, and knowledge is also the ability to create new information. And over time, knowledge can be accumulated and put into human context, combined appropriately and applied, and that results in wisdom. So we are humans here. This is how, I also put measurements at the bottom over the physical world, because this is what we need in order to observe data. But now machines are catching up. Machine can do a lot better measurements than us, also collect data, also create information. So as Daniel pointed out, our role is really at the top of the pyramid, like in strategy and wisdom, and let machines do the jobs that they can do better. I can only see visible spectrum, but machines can do radio waves, ultraviolet, X-rays. Machine can all the acoustic spectrum. I can only hear very small. So also other measuring particles and waves, machines are much better. So let machines do this part at the bottom, and we move up the pyramid. And this is also what I call the scientific method. What is the scientific method? We make observation, generate data, and make predictions. And based on predictions, going according to the hypothesis or not, we kind of make changes and go the cycle again. So this is how we have evolved. But now we need to move up, because we have machines that are created by our wisdom and knowledge. They are helping us to do much better job here. So how it's going to look like is, so this is, the 5G network, in my view, is going to be the backbone in making this thing happen, what I called network wisdom or network sapiens. So we are going to, we evolve from Homo sapiens, wise man, to network sapiens or network wisdom. So machines are catching up, but we should not worry at this point to changing our name. We can still keep it Homo sapien, because there's still a role for being wise and for wisdom, at least during our lifespan. But in the future, who knows, machines are able to even be much wiser than us. So how this is going to look like? Communications or access always have been to access to the information. Humans trying to access the information. But right now, I think in the very first presentation on satellites, we learned like 2/3 of the humankind does not have access to the internet, wired or wireless. So how we are going to make that happen? So we need to first solve a big problem there. And then also now, more and more, humans are going to create data, information, and knowledge. We kind of heard about the user-generated content and so on, many different scenarios. And then machines, sensors creating data that needs to be captured, and then this 5G network will bring it to the cloud. And similarly, things or machines accessing the information to generate value. So this all hopefully will result in this network sapiens that I'm putting together, enabled by this 5G and cloud, that can help us solve the top problems facing humanity. So how we are going to do that? This the backbone network. So, since I'm giving a talk at an academic institute, I need to show a plot to get attention of the audience. So I have this plot. What I call connectivity omnifications. Omnify is order of magnitude increase every 5 years. With this rule, it's very simple to understand things. Many people have been saying 10x, 1000x. With Omnify, 10 times every 5 years. That means in 10 years, 100 times. In 15 years, 1,000 times increase. So anything that matters in the ICT industry has followed this trend. If you look at the storage capacity increase in million times over 30 years, computing power increase in million times in 30 years. Similarly, now mobile data is doing the same thing. We expect to go peak data rate to go from 1 megabits per second with 3G in 2000 to 1 terabits per second with 6G in 2030. So when in the very first presentation, the affordability was mentioned. We cannot connect everybody in the world if the cost is very high. So if we stay on this trend, similar to the Moore's law, then we can make the cost per byte cheap enough to connect whole humankind. So another thing I'm putting here is number of the things. I mean, there are many predictions. I mean, there's a race to come up with the biggest number. So I said, okay, let me come up with I want to win that race. So I put in this 20 trillion things. But then, I mean, this morning at the start, Al mentioned that he just hosted an event here at UCSD, trillion sensors. So I was very much encouraged. So I also earlier pointed out if IoT is a hype or it's going to be a reality. I mean, if IoT is on this curve, anything that matters, you can go and look at anything that matters in the IC industry has to follow this rule. I mean, this is very similar to the Moore's law, but Moore's law is very complex for the common person to understand. Like 2 times every 18 months, I run into problems. I did not go to as good school as UCSD. I cannot do the math, but 10 times every 5 years, powers of 10s are much easier to do. So just remember that. So if IoT is going to follow this curve, then it's going to matter, and this is going to be true. I mean, this number, like in 2020, it looks very big, $200 billion. But what I'm saying is, for me, things are sensors, accessories, and other non-hub devices. They does not need to be directly connected to the internet. For example, take example of cars. Today, cars have 75 to 100 sensors each car. In 2020, is expected there will be 200 sensors in each car, and there will be 110 million cars sold in 2020. That's, I mean, 220 billion sensors just right there. 22 billion, sorry, 22 billion. And then, I mean, similarly, we have seen putting sensors in crops and medical, transportation, and other industries. So these numbers, I mean, are not very, very big in that respect. So, as I said, we want to make this affordable, and I want to solve the biggest challenges that humanity is facing, and energy is the #1 challenge. Today, the world's data centers consumes as much power as UK as a country, and it's increasing, and we saw some of the base station power numbers. It's in tens of megawatts hours every year, and there are millions and millions of base stations. So if now I'm saying I'm going to make this omnification, and then I kind of make the energy problem worse, I do not want to do that. So how we can kind of not create problem, but rather focus on solving the problem. So let's look at, I mean, so I show a plot to get the attention of the audience in an academic institute, and I also know to get a respect in an academic situation, you also need to show a few equations. So I've put together some of the equations here. I think everybody knows about Maxwell. Maybe not many people know about Maxwell's demon. So this is Maxwell actually proposed this thought experiment. There was, gas at a certain temperature in a chamber, and then you put a wall and tiny trap door and put a tiny demon there, and it can observe, temperature is simply the average kinetic energy of the molecules, and this demon can allow the faster molecules to kind of come to this side, open the door when a faster molecule is coming here, and then the slower this side. So the total energy of the system will be the same. You don't violate the first law of thermodynamics, but sometimes you contradict the second law of thermodynamics, that you have created order and reduced entropy in the system, and now you can generate energy because you can put a heat engine or a turbine from the hot side to the cold side. But so this thought experiment, people have been thinking about it for about 130 years, and now we have some understanding. This is not, we can do this. It's not like there will be some energy spent in opening and closing this tiny door. That can be made infinitely small, but it turns out now we have this understanding, relationship between physics, information theory, and theory of computation. Actually, information itself means energy. So how much energy information has? One bit has this much energy. K times T log of 2, that's this much joule. And how much energy is world's total information? We earlier saw it's in zettabytes. 10 zettabytes is world's total energy. How much is that in terms of power? I mean, that's just 230 joules. That's 230 watt per second. So that means you have 460 watt light bulbs, just light them for 1 second, that's all. I mean, that's the energy. I mean, so if I want to know with Internet of Things, sense these things, create information, sensing information, energy cost is very, very small, as you can see here. But what about transmission? I think we say, okay, now I can capture, because I said, now you need to do universal capture of information, not only the access. So I can capture this information with very, very low power or energy. But what about transmission? We always know, okay, this is R square law. I mean, we are, as human, evolved by kind of following that law. For example, if I cannot listen to somebody speaking clearly, I move closer because then the signal strength gets better and so on. But this is, I mean, when we started looking at millimeter wave, myself and my colleagues, the first realization was this, actually when you go higher in frequency, because there's a misconception that somehow there will be higher propagation loss. That is not true. Actually, it's the other way around. I mean, you can see that. I mean, if this is your antenna area, and you want to reach a certain distance, and the higher the frequency, smaller the wavelength, more concentrated your energies. For broadcast, that was true, that R square law, but for directional transmission, higher frequencies are better. So that means I can be very energy efficient. Most of the communication is unicast. I can just direct the communication at the target. So what about the cost of transmission? So I want to create this connecting every being and everything, creating this network wisdom. But I need to transmit information from these sensors and things, and also accessing information. I'm saying we need terabits per second data rates or capacities in the next 15 years. So there will be a lot of cost, you think. But if you think this R square law does not apply, there's in free space, if I can send a photon, this is the light photon, I can send this from here to the other end of the universe and come there at the same energy. There is no loss of energy when things propagate in free space. It is just because when we have a transmitter, we spread in all directions, and that's how the loss is. The area of a sphere is proportional to the R square. But if we do directed transmission, which is possible, you can do more and more directed transmissions, but by going higher in frequencies, you can go much farther with very, very low energy cost. So in theory, you can also make that cost zero, but very, close to zero. So, okay, why, what I call it going small for big gains. Let's look at the antenna sizes from 1 gigahertz to like 120 gigahertz frequency, how big these antennas are. It turns out that at 1 gigahertz, your antenna size is over 7 meters. This big thing is like 7 meters squared. So you want to get 30 dB gain. I said you want to make this transmission directional, you need to have this big size antenna. I guess everybody has a Samsung 85-inch ultra-high definition TV at home, so put like 3 or 4 TVs together, that is the size. But once we go like at 20 or 30 gigahertz, it's just to get 30 dB gain, size is just, this much or smaller than this. Now I can put this size array in a small base station. This is very much feasible. I cannot put this size array in this. We say, okay, spectral reuse going small in size, but I'm contradicting. If I stay at low frequencies, that has been the hype with small cells. I said I can go small in cells, have spatial reuse, but I had a 17 dB antenna gain with the bigger sectors. But now I go smaller, my antenna aperture is becoming smaller. I'm no longer directive. So I'm now again broadcasting energy in all directions. So this small cells doesn't go well with low frequencies. They go well with the higher frequencies where I can actually make my radiating elements smaller. And you keep going higher in frequencies, your size becomes a smartwatch at 60 gigahertz to get 30 dB gain and so on. Or other ways, you give up on gains. At 1 gigahertz, you can get a lower gain by making your antenna smaller. So So what this means, I mean, going small for big gains, you get gains in coverage because you can go longer now, in capacity because your beams are very directive now, you can have frequency reuse, and also in power efficiency. I mean, all the three performance metrics that matters in cellular or in mobile communications, you can get the best of those by going small, by going higher in frequencies because of this relationship. Aperture area is directly proportional to the wavelength. Higher the frequencies, smaller the wavelength. And this also we say backhaul is the problem, but once you have directive transmission, you can use the same spectrum for the backhaul beam going to the other base station and also for the access. So backhaul and access can coalesce together and also enable small cell deployments. At high frequencies, as I pointed out, you say, okay, you want to make cells smaller, put them on light poles and anywhere, but if your antenna is this big to get gains, I mean, that's not possible. This is physics. I mean, we cannot fool around with physics. I can solve engineering problems, but not fool with physics. And this is why we say, okay, going higher in frequencies, you have higher spectral efficiency due to the reasons I mentioned, and also a lot more spectrum available. And this enables you to get the coverage capacity and power efficiency. And I have actually 2 minutes video to show. Can I? Yeah. So. The video is about our 5G millimeter wave demo that we did last month, about 1.2 gigabits per second at 110 kilometers per hour and 7.5 gigabits per second peak data rate. Let me see if this is connected to the sound system. Thank you.